All right, Module 7. Um, so Module 7 is all about rotating around bonds and then making different conformations of molecules. Um, this is probably the first topic that wouldn't have been covered at all in a Gen Chem class. So probably most of you have never done anything with this before. You're going to want to use molecular models when you do this module. We've got plenty in the room. Use them, build them, look at them while you read stuff online, while you watch videos online, have a model in your hand. It'll just make life a lot easier. So the first question is, why can some bonds rotate? I mean, I said this is all about bond rotation. And if you think about the bonds we've talked about, the simplest kind of bond, the single bond, is what we call a sigma bond. So remember that sigma bonds are made of two hybrid orbitals, which are essentially kind of like cylinders, and they're pointed at each other. All right, so sigma bonds are what we call cylindrically symmetrical. Meaning you've got two orbitals on neighboring atoms pointed at each other along one axis, and if you rotate along that axis, they're still overlapping. So rotating around the bond axis doesn't change the overlap between the orbitals. And so if you build a model, you'll see if you have a single bond, you can just keep rotating around any one of those single bonds, and the bond stays together. All right. So then what would cause me to not be able to rotate around a bond? Well, a double bond. Double bond has a pi bond. All right. And a pi bond is not cylindrically symmetric. All right. Remember, pi bond is overlap of parallel p orbitals. And the word parallel is important there. I need my two p orbitals to be lined up in such a way that they overlap. And if I start rotating around the bond, it's going to break my pi bond. So I have a couple of models. I'm going to break this up and try and do the little webcam video. Okay, so what I have here is a model of a pi bond, two parallel p orbitals. If I start to rotate around the bond, they don't overlap anymore. All right, I'll show it from this angle, then I'll show the class. I'll show it from this angle. If I have my two p orbitals like this and I start rotating, they no longer overlap. And so, in other words, I have to break the pi bond in order to rotate around the sigma bond. Okay? Now I'm showing the class. If I take my pi bond, I start rotating, the p orbitals are no longer parallel. And if the p orbital is no longer parallel, I've effectively broken my pi bond. All right? So rotation around a double bond actually requires breaking of the pi bond, which is hard to do. It's a bond. Bonds are hard to break. So pi bonds essentially lock the molecule in one position. All right, there's one other situation where you're not going to have free rotation around bonds. You might have some rotation, but not free rotation around bonds. Anyone think of a separate situation that would prevent me from rotating around a bond? It doesn't involve pi bonding necessarily. A cycle, having rings, cyclic molecules. You can prove this to yourself pretty easily. If you make a ring of atoms and you try and rotate around bonds, there's going to be some freedom of rotation, but the ring prevents you from freely rotating. So if you have, say, a 5-membered ring or a 4-membered ring, each bond might have some flexibility, but it's not free rotation. So we'll actually come back to those situations where bonds can't rotate later. What we're going to spend the first half of this module talking about is, all right, when bonds can rotate, what effect does that have? Where do they spend most of their time? And how do we analyze them? All right, so I asked everyone in the room to build a model of butane. If you're watching this, you should build a model of butane. Model of butane will look something like this. So 4 carbon atoms in a chain, 10 hydrogen atoms. Where would you find butane? Yeah, where would you find it? You can get this in most stores. What product would it be in? Yeah, a lighter. Yeah, a lighter for a grill, cigarette lighter. You can find butane in those. All right, so what I want you to notice is, with the model in your hand, try rotating around bonds. There's a bunch of single bonds there. Try rotating around any of them. What I've kind of represented on the board is rotation around the central carbon-carbon bond. So note that you can rotate around the central carbon-carbon bond, but you can rotate around the other carbon-carbon bonds as well. And now if you look directly down the bond axis for any of those bonds, what I want you to notice is how do atoms line up as you rotate around. So I made some models of this looking down the central carbon-carbon bond. So if you look down the central carbon-carbon bond in your model, so hold it so that your eye is going straight down the bond. And look at how the other atoms bonded to those 2 carbons line up. And if you rotate around that bond, you'll see that the relationships of the other atoms changes. Okay? We have what we call 2 different main conformations we can make. We call it the staggered conformation and the eclipsed conformation. In the staggered conformation, you'll notice there are no 2 things right on top of each other from your point of view. In the eclipsed conformation, each atom on the front carbon lines up with an atom from the back carbon. So I want you to, with the model in your hand, show yourself a staggered conformation, show yourself an eclipsed conformation. Yeah, in a staggered, you can see all 6 groups, right? There's 3 groups coming off the front carbon, 3 groups coming off the back carbon. In a staggered conformation, you can see all 6. In an eclipsed conformation, you really only see the 3 in front, and they're kind of blocking the ones in back, which is what eclipsed means. Does everyone successfully seen that for themselves. All right. And so we can actually, do a full rotation. I've got this set up so I can show full rotation all the way around. And you'll notice if you rotate all the way around that bond, you go through several staggered and several eclipsed conformations. As the angle between those two methyl groups changes. All right? So what we want is a way that we can actually analyze those different things. So someone named Newman, I guess, probably not the guy from Seinfeld, but probably another Newman, came up with a way to represent these. They're called Newman projections. And what Newman projections are is just a way that we represent the different conformations. All right, we call each of these different positions a conformation of the molecule. So when we use the term conformation, those are different ways to arrange a molecule based on rotation around bonds. So this is different from like isomers, where you can have different ways that they're bonded. Here we're talking about the same molecule. Every picture I drew here, every one of these pictures in this little animation represents the same molecule. It's just we're rotating around that central bond and getting a different view of it. So conformations are different ways to arrange the same molecule based on bond rotation. And when we want to analyze them, we use these Newman projections. All right. So in a Newman projection, we have a circle. We have three substituents represented with their bonds going straight to the center of the circle. All right. So this point here represents the central carbon, or the carbon in front. All right. This represents the front carbon. And then those other three lines that come out of the circle, those represent the substituents on the back carbon. So it's like that circle is showing like, the back carbon is blocked from our view, so we can only see the bonds coming out from it. And this Newman projection on the left, would that represent a staggered or an eclipsed conformation, do you think? It's staggered. So this is a staggered conformation. And this over here would represent an eclipse conformation. Now, in an eclipse conformation, we don't want to draw the substituents on the back carbon directly behind the ones on the front carbon, because then we wouldn't be able to see them. So we draw them a little bit off to the side. So these Newton projections are just the way we're going to represent the molecule. Now, if you had to guess, which of these two would you think the molecule prefers to spend its time in? Staggered conformations or eclipse conformations? All right, why? I had a couple people say staggered. Why'd you say staggered? All right, because the nuclei are as far apart as possible. It turns out the nuclei, since they're kind of buried in the center of the atom, they're not really what's driving it, but it's the electrons on the surface, yeah. So when we want to think about different conformations and where a molecule is going to spend most of its time, the idea is big groups being close together, the electrons on the surface of those groups repel each other. Okay? And when the electrons on the surface repel each other, that means they'd rather be farther apart. A conformation is higher energy or less stable when you have big groups close together. The bigger the groups are, the worse that interaction is. All right, so it's fairly common sense. But molecules are going to prefer staggered conformations to eclipse conformations because it allows those electrons on the surface of each group to be farther apart. All right, so staggered versus eclipsed, staggered is always going to be better. If we go back and look at this molecule, there are still several different kinds of staggered conformations we could have. We could have this staggered conformation where the two methyl groups are as far apart as possible, or we could have this staggered conformation. You know, this is still staggered, but where the methyl groups are getting a little closer together. All right, if you had to guess, which of those two would you say is more stable? The first one, where they're across from each other. Yeah. So we actually have a name for that as well. So not only do we have staggered versus eclipsed, but among staggered conformations, we can have situations where two groups are only 6 degrees apart. And I don't know, someone French named this. And it was like, hey, how many people know the word gauche? What does the word gauche mean? All right, left. But it also it has another connotation. It's not just left. It's like tacky, a little weird, like inappropriate. Like if you had an awkward interaction with someone, they might, oh, that was really gauche. It's one of these. It's kind of like a fancy way to say awkward. So gauche interactions are these awkward interactions where the two groups, they're not eclipsed. Eclipsed would be like really bad, but this might be like you get on you have a close talker. You're in a conversation with someone. Oh, bring you back to Seinfeld. I don't know if you've ever seen the Close Talker episode, Seinfeld, but there's one where there's someone who likes to get right up close to talk. So here, and that's kind of tacky, kind of awkward. So this is what we would call a gauche interaction. So that means two groups are 60 degrees apart. For butane, actually, this other one where they're across from each other, we call that an anti-conformation. When they're across from each other, we say it's an anti-conformation. So when you hear the terms gauche and anti, that's what they're referring to. And it turns out gauche interactions, as you might suspect, they're somewhat unfavorable. So if you think about that butane molecule that you have in your hand, hopefully if you're watching this, it's going to rotate freely. At room temperature, each bond in that is going to rotate freely because there's enough thermal energy and things are always moving that it's going to rotate a lot. But what it'll do is spend more time in the lower energy conformations. So it's going to spend most of its time in this conformation on the left, the anti-conformation. It'll spend some time in the gauche conformation. And notice for butane, there are two gauche conformations. There's one there, and there's another one there. But the way this molecule is going to behave is probably it's going to spend most of its time here, and most of the time it might kind of rock back and forth a little bit from the anti-conformation. Imagine this happening at, 1,000,000 times faster than I'm showing it. But it might rock back and forth, but then every once in a while it swings past the eclipse conformation and swings over to the gauche conformation and stays there for a little bit. Every once in a while it'll swing past that and get over to this other gauche conformation, and then it'll swing back to anti, and it'll just spend more time in that anti-conformation. On the whole, it's going through all the conformations, but it's spending most of its time in the most stable one. All right, less time in the less stable ones. Eclipse conformations, those are really the highest energy points on its rotation, so it spends almost no time in the eclipse conformation because it kind of like slides right past that. Okay. When you have other molecules, so now this molecule up here is no longer butane. This is actually 2-methylbutane. So if I had 2-methylbutane and I'm looking at it, my point of view is to look down the bond this way. So then on my front carbon, I have a methyl group and 2 hydrogens. On my back carbon, I have 2 methyl groups and 1 hydrogen. Then we have situations where in the conformation on the left, I have not one but 2 gauche conformations. Right? Here's a gauche conformation where these two are bumping into each other. And then on the other side, this methyl group's bumping into the other one. So if I compare these two conformations, two gauche interactions is worse than one. So, the situation on the left is when you have, I don't know, you got on the subway and you were sitting there and then someone sat down to the left of you and someone sat down to the right of you and both of them kind of leaned in your direction. Yeah. Unfortunate situation. So that's worse than just having that gauche interaction on one side. So the point is, 2 gauches are worse than 1. So that's how you would analyze the conformations of a molecule. For any molecule, you can go through and draw 3 different staggered and 3 different eclipsed conformations around each bond. And you can think about what's the most stable one, what's the least stable one. And that'll tell you where the molecule spends more time and less time. Questions about Newman projections? I mean, there'll be more examples when you do the skill builder, but it's all really the same idea. Yep, question. So the question is, why are there only 3 bonds shown in the Newman projection? Like carbon usually forms 4 bonds. The 4th bond is the one that's going directly into the page. So you're always directing your eye so that there's one bond that you can't see because you're looking straight down the axis of that bond. Okay, so that, yeah, we only see 3 bonds because the 4th one is the one that's being hidden from our point of view because we're looking straight at those 2 atoms. Yeah. Question? All right, the question is, how do you know, given a skeletal structure, how do I draw the Newman projection? All right, good question. So really you have to analyze one bond at a time. A Newman projection is only useful to analyze one bond at a time. So step 1 is pick a bond. A lot of the time you'll be told what bond to look at. All right. So, for example, I might give you this molecule and ask you to analyze it. Now, I see 1, 2, 3, 4, 5 carbon-carbon bonds that I could analyze. Usually what I'll do is I will say, specifically, look down one specific bond. So I'll make some attempt at drawing like a little eye, like this. Ooh, there's a little eye. Maybe it's got eyelashes. I don't know. And I'll draw a little arrow to say, okay, look at it from that perspective. But if you're just, given a molecule, if you're just trying to analyze a molecule on your own, you've got to pick the bond to analyze. But for any problem I give you, I'll usually tell you which bond to analyze. And so then, once you've picked a bond, you've got to identify the substituents on the front carbon in that bond and the back carbon. And the question is, what do I mean by substituents? I mean, yeah, whatever groups it's bonded to. All right. So, for instance, I'll do the front carbon in purple here. All right. So my front carbon is right here in purple. And say, all right, what is the front carbon bonded to? Well, what's not showing? How many hydrogens? 2 hydrogens. So the front carbon is bonded to 2 H's. And what else is it bonded to? 2 C's. Now, specifically, all I care about is the third substituent. I don't care about the bond that I'm analyzing. So it's bonded to a methyl group. If you haven't picked up on it yet, I use the abbreviation for methyl group, ME, a lot. Mainly because I'm a narcissist, but also because it takes slightly shorter amount of time to write ME than it does to write CH3. So whenever you see ME, that means methyl. So yeah, this front carbon is bonded to 2 hydrogens and a methyl group. All right. So what I'm going to do is draw a circle. And from the perspective that I've chosen here, if my eye were actually in the board where I drew this eye, and I were looking at the molecule like that, then this bond to the methyl group that's in the plane of the board and pointed in the direction it's pointed, what direction would that be going compared to my eye? Up, down, into the page, out of the page? It's going straight down. Yeah. So I'm going to draw the bond to the methyl group going down. And then my other 2 bonds are going to be 120 degrees apart from that, and those are both going to the hydrogens. All right, now I look at the back carbon. The back carbon seems to be where the action is. The back carbon I'm going to do in green here. What substituents do I have on the back carbon? What are the 3 things coming off of that green carbon? A Cl, a methyl, and then a bond to a 2-carbon group, which would be an ethyl group. How do you think I would abbreviate ethyl? ET. We'll use that abbreviation a lot too. I mean, that saves us a lot, right? To write ET instead of writing C2H5. Who wants to write all that? So my 3 substituents on the back carbon are methyl, ethyl, and chlorine. All right. And now I want to think about, okay, what direction is each of those going? So from my perspective, again, the bond that's in the plane of the board, if I'm looking at it from where the eye is drawn, should be going straight up. So straight up, I'm going to draw a line. Remember the lines on the back carbon come out of the circle. They don't go all the way to the center. I'm going to draw the ethyl group there. And now I can even think, all right, if my eye is actually in the plane of the board, whatever's coming out of the board corresponds to which of my hands? My right hand. So that methyl group should be going down and to the right. And the thing going into the board corresponds to my left hand, which I can't actually extend through the wall. But if we were going into the board, that would be on my left. So down and to the left, that's where I'm going to draw the chlorine. And so now I see, well, in this conformation that I've drawn it, I've got a gauche interaction between chlorine and methyl, and a gauche interaction between methyl and methyl. I encourage you to use that little emphasis when you say gauche. So there I've got two awkward interactions. I've got a chlorine-methyl gauche interaction. And I've also got a methyl-methyl gauche interaction. And then once you've drawn one Newman projection for the molecule, the rest of them just follow. What I usually do is keep the front carbon the same and just rotate the back one. So keep moving the substituents in the back one by 60 degrees at a time. Yeah. So then, if I wanted to analyze this, if I wanted to then like draw, okay, what's the next conformation? Well, I'd have to ask myself, am I considering the eclipsed ones too, or just the staggered ones? But I would start by drawing my front carbon substituents in the exact same spot. Let's say I was just going to rotate by 60 degrees. Now it's going to be eclipsed, and I would rotate, say, the chlorine to right up here, eclipsed with the hydrogen. The ethyl group would come down here and be eclipsed with the other hydrogen, and then the two methyl groups would be eclipsed with each other. And then I would just keep doing that. So I'd encourage you to use models for this at first, and then once you get comfortable with it, you really don't need the models. But that takes a while. So the question is, are these more gauche than the other ones? Yeah, these are even worse than gauche. What's worse than gauche is like being eclipsed. So that's like being eclipsed is more like you sat down on the subway and then someone came and sat on your lap, right? That's like really bad. So these are eclipsed interactions. Yeah. Any other questions about Newman projections? I think I'll call it a day there. We'll do more next week.